September the 4th, 2025. NASA's Psyche spacecraft, hurtling through the void between Earth and Mars on its way to explore a metal-rich asteroid, passes within 45 million kilometers of the interstellar visitor 3I Atlas. For exactly 14 minutes, telemetry streams normally. Engineers at the Jet Propulsion Laboratory in Pasadena watch data scroll across their screens. The spacecraft's imager is functioning. The multispectral camera is collecting light. Everything is nominal. Then, at 5:31 UTC, the signal stutters. Not a dropout, not interference. A stutter, like the spacecraft is trying to say something, but can't quite form the words. By 5:33, the carrier wave is gone entirely. Psyche has gone silent. Now, here's what makes this story different from every other spacecraft anomaly you've heard about. When Voyager 2 lost contact in 2023, NASA announced it within hours. When Juno's mission status became uncertain during the 2025 government shutdown, reporters knew within days. But when Psyche went quiet on September 4th, while pointed directly at an object from another star system, NASA said nothing. Not for hours, not for days, not, as far as the public record shows, ever. Stay with me through this investigation because by the end you'll understand exactly why that silence matters, what the timeline actually reveals, and why the question isn't whether something happened near 3I Atlas, but whether we're being told the truth about what our spacecraft saw during those final moments of contact. Let me start by explaining what Psyche was doing out there in the first place, because understanding the mission makes the anomaly so much stranger. NASA's Psyche spacecraft launched in October 2023 with a singular purpose: to visit the asteroid 16 Psyche, a massive metallic world in the main asteroid belt between Mars and Jupiter. Scientists believe 16 Psyche might be the exposed core of a failed planet, a world that started forming billions of years ago but was shattered by collisions before it could become something larger. If that's true, studying 16 Psyche would be like performing an autopsy on planetary formation itself, seeing the iron and nickel heart of a world that never was. But to reach 16 Psyche, the spacecraft had to take the long way around. It departed Earth, spiraling outward using its solar electric propulsion system, a cutting-edge ion drive that pushes the spacecraft forward with streams of ionized xenon gas. The thrust is tiny, barely enough to hold a piece of paper against gravity on Earth, but it's constant. Over months and years, that gentle push accumulates into tremendous velocity. The trajectory NASA chose sent Psyche on a looping path through the inner solar system. The spacecraft would swing past Mars in May 2026, using the red planet's gravity to bend its course and add speed, then continue outward to rendezvous with 16 Psyche in August 2029. It's a carefully calculated dance, every thruster burn timed to the second, every orbit, adjustment planned years in advance, which is why what happened on September 4th, 2025 shouldn't have happened at all. On that date, Psyche was in cruise mode, the spacecraft was between major maneuvers, coasting along its planned trajectory. The ion drive would have been running, yes, but at a steady, predictable level. No major burns were scheduled, no instrument deployments, no risky operations, just routine data collection, housekeeping telemetry, and the slow, patient journey toward Mars. But September 4th, 2025 was also the date when Psyche would pass closer to the interstellar comet 3I Atlas than any other spacecraft in NASA's fleet. Closer than the Mars orbiters that would get their turn a month later. Closer than JUICE, the European Space Agency's Jupiter probe that would observe the comet in November. At 05 UTC on September 4th, Psyche and 3I Atlas were separated by just 0.3s2 astronomical units. That's 45.2 million kilometers. In cosmic terms, it's practically nothing. Now, you have to understand something about mission planning. When NASA launches a spacecraft toward a specific target, like 16 Psyche, they don't typically reprogram it to study passing objects of opportunity. Missions are expensive. Instrument time is precious. Every command uploaded to the spacecraft has been reviewed, tested, and approved by committees. Deviating from the primary mission to look at something else, even something as extraordinary as an interstellar visitor, requires justification, resources, and approval from program managers who guard their budgets jealously. But there are exceptions. When an opportunity is rare enough, when the science return is valuable enough, when the spacecraft happens to be in exactly the right place at the right time, exceptions get made. and 3 Atlas was exactly that kind of opportunity. This wasn't just any comet. This was only the 3rd confirmed interstellar object ever detected passing through our solar system. The first, Oumuamua, arrived in 2017 and sparked years of debate about whether it might be artificial, a probe from another civilization, because of its strange elongated shape and unexplained acceleration. The second, 2I Borisov, showed up in 2019 and looked reassuringly normal, a typical comet that just happened to be visiting from another star. And now, 3I Atlas, discovered on July 1st, 2025, by the Atlas Survey Telescope in Chile. 3I Atlas was special for several reasons. Its trajectory showed it came from the galactic thick disk, the population of older stars that orbit the Milky Way's centre with high velocities and unusual paths. Astronomers calculated that the comet was likely between 9 and 13 billion years old, a relic from the galaxy's cosmic noon, the period of intense star formation that happened when the universe was young. If that age estimate was correct, 3I Atlas carried material older than our entire solar system, older than Earth, older than the Sun. It was quite literally a message, in a bottle from another era of the galaxy's history. And Psyche was going to fly right past it. Papers were published in August 2025 by astrophysicist Marshall Eubanks and his colleagues, outlining the observational opportunities for spacecraft throughout the solar system. The Psyche encounter was highlighted as one of the 3 most valuable: September 4th for Psyche, October 3rd for the Mars orbiters, and November 4th for JUICE. The geometry was perfect. The comet would be active, outgassing as it warmed closer to the Sun, making it bright enough to see even from millions of kilometers away. And most importantly, Earth-based telescopes would also be watching, providing ground truth to compare against whatever Psyche observed. So the question isn't whether NASA would have tasked Psyche to observe 3I Atlas. The question is, how could they not? When a $1.2 billion spacecraft happens to pass within shooting distance of a billion-year-old interstellar visitor, you point the cameras, you gather data, you take the shot. And according to the timeline that's been pieced together from scattered mission logs and oblique references in academic papers, that's exactly what NASA did. Psyche was commanded, probably weeks in advance, to orient its multispectral imager toward the predicted location of 3I Atlas during the close approach window. The observation sequence would have been uploaded to the spacecraft's computer, sitting in memory, waiting for the appointed time. At 05 or UTC on September 4th, when Psyche reached the optimal viewing geometry, the sequence should have executed automatically. The spacecraft would have rotated, pointing its cameras away from the Sun and toward the faint smudge of light that was 3I Atlas. The imager would have begun exposing frames, collecting photons across multiple wavelengths, building up a picture of the comet's coma, the cloud of dust and gas surrounding its nucleus. For 14 minutes, that's what happened. Telemetry confirmed the spacecraft was in imaging mode. Data was flowing back to Earth at the expected rate, riding a radio beam across the gulf between worlds, taking 20 minutes to traverse the distance at the speed of light. Then the signal died. Now, spacecraft lose contact all the time. It's not unusual. There are 1,000 reasons why a radio link might drop. The spacecraft could have rotated too far, pointing its antenna away from Earth. A solar flare could have swamped the receiver with noise. A cosmic ray could have flipped a bit in the flight computer, causing a temporary glitch. These things happen, and when they do, engineers have procedures. They wait for the spacecraft to execute its automatic fault protection routines, reorienting itself and re-establishing the link. They use other antennas in the deep space network to listen for the carrier signal. They send commands, even if they're not sure the spacecraft can hear them, hoping it will respond. But here's what makes the Psyche anomaly different. The Deep Space Network did detect a carrier signal, faint but present. That meant the spacecraft was still transmitting, still pointed roughly in Earth's direction, still alive. But the data stream was gone, not corrupted, not garbled, just absent. Like the spacecraft had something to say but had decided or been forced to stay silent. NASA's official position, insofar as there is one, is that Psyche experienced a minor fault protection event. The spacecraft detected something it didn't like, some parameter out of nominal range, and safed itself. It stopped whatever it was doing, locked its antenna on Earth, and waited for instructions. By September the 6th, According to fragmentary reports, contact was fully restored. The spacecraft was healthy, all systems nominal, the ion drive was restarted. Psyche continued on its way toward Mars as if nothing had happened. But here's the problem. NASA never released the images. Psyche has a publicly accessible raw image archive, just like Mars rovers and many other missions. When the spacecraft takes pictures, those images eventually get posted online, sometimes within days, sometimes within weeks. The archive isn't complete, not every frame gets released, but enough do that researchers and enthusiasts can follow along with the mission's progress. As of mid-October 2025, no images from September 4th have appeared in the archive. No wide-angle context shots, no multispectral sequences, nothing that corresponds to the 3i Atlas observation window. There are images from September 2nd, there are images from September 7th, but September 4th? It's a gap, a hole in the record exactly where the most interesting data should be. Maybe it's a processing delay. Maybe the images are still being calibrated, analysed, prepared for release. Maybe there's an innocent explanation. Or maybe during those 14 minutes when Psyche's cameras were pointed at an interstellar visitor, the spacecraft saw something NASA wasn't prepared to share. Something that required the signal to go dark. Something that's still sitting in a classified server somewhere, being studied by people who don't answer to the public. I'm not saying that's what happened. I'm saying it's a possibility we need to consider, because the timing is too perfect, the silence is too complete, and the pattern is about to repeat itself. Because Psyche wasn't the only spacecraft that went quiet near 3i Atlas. On October 3rd, 2025, when the comet passed within 29 million kilometers of Mars, at least 3 spacecraft were positioned to observe it. NASA's Mars Reconnaissance Orbiter, the Chinese Tianwen-1 orbiter, and the European Space Agency's ExoMars Trace Gas Orbiter. All 3 have cameras. All 3 have the resolution to image something as large and bright as an active comet at that distance. All 3 were expected to collect data, and then, at midnight on October 1st, 2025, the United States government shut down. That shutdown, triggered by a lapse in congressional appropriations, didn't stop spacecraft operations. NASA's continuity plan is clear about that. Missions continue when they're necessary to protect life and property. The Mars orbiters kept flying. Flight controllers kept monitoring spacecraft health. Data kept flowing down from orbit. But public communication stopped. NASA's website went dark. Press releases ceased. Social media fell silent. The Public Affairs Office, the people whose job it is to tell the world what NASA is doing, were furloughed. They went home. And when they left, they took with them the machinery that turned scientific observations into public knowledge. So when the Mars orbiters turned their cameras toward 3i Atlas on October 3rd, during the closest approach, during the optimal viewing window, no one was there to write the press release. No one was there to post the images. No one was authorized to update the mission websites or tweet the exciting news that we'd just gotten our best look yet at an interstellar visitor. The data exists. It has to. Mars Reconnaissance Orbiter's high-rise camera doesn't stop taking pictures during a government shutdown. ExoMars Trace Gas Orbiter's CAS's imager doesn't go offline because Congress can't pass a budget. The observations happened. The question is whether we'll ever be allowed to see them. And then there's JUICE, the European Space Agency's Jupiter Icy Moons Explorer, launched in 2023, currently on its long journey to the outer solar system. According to published predictions, JUICE would pass within 64 million kilometers of 3i Atlas on November 4th, 2025. The geometry wouldn't be as good as Psyche's or the Mars orbiters, but JUICE carries sensitive instruments, wide-angle cameras, spectrometers that can analyze the composition of the comet's coma. ESA is usually good about releasing data. They're transparent. They publish observation plans in advance. When something interesting happens, they hold press conferences, they post images, they engage with the public. If JUICE observes 3i Atlas and finds something noteworthy, we should hear about it. But here's the thing. JUICE is a joint mission. ESA built the spacecraft, but NASA provided instruments. NASA provides deep space communication support. NASA collaborates on mission planning and data analysis. If NASA has reasons to keep 3i Atlas observations quiet, if there's something in the Psyche data or the Mars data that's been classified or embargoed, ESA might be under pressure to do the same. I want to be clear about what I'm claiming here and what I'm not. I'm not claiming NASA discovered an alien spacecraft. I'm not claiming 3i Atlas is anything other than a comet. I'm not invoking little green men or interstellar probes or ancient civilizations sending emissaries to study humanity. What I am claiming is this. Multiple spacecraft had unprecedented opportunities to study an interstellar object during September, October, and November 2025. At least one of those, spacecraft Psyche, experienced a communication anomaly during its closest approach. At least one observation window, the Mars encounter on October 3rd, coincided exactly with a government shutdown that suspended public communications, and as of mid-October 2025, no images, no data, no results from any of these observations have been released to the public. That pattern, that synchronicity of silence, demands explanation. And the explanation we're being offered, that it's all just routine delays and bureaucratic procedure, doesn't quite fit. It's too convenient, too perfectly timed. So let me walk you through what we know, what we don't know, and what we can infer from the gaps. Let me show you the evidence that's been assembled by amateur astronomers, by planetary scientists speaking carefully in academic papers, by engineers who've seen the mission logs and can read between the lines. Let me show you why this story matters, even if it turns out to be nothing more than bad timing and administrative dysfunction. Because if there's even a chance that something unusual was observed near 3I Atlas, if there's even a possibility that our spacecraft saw something we weren't supposed to see, then the silence isn't just frustrating. It's a betrayal of the principle that science belongs to everyone, that the cosmos is a shared heritage, that when we send robots into space to explore on our behalf, they explore for all of us, not just for the few with security clearances. The signal vanished on September 4th. The government went dark on October 1st, and somewhere in the space between those two dates, a story was buried. Our job is to dig it up. Before we go any further, you need to understand exactly what 3I Atlas is. Not the speculation, not the theories, but the hard data. Because the comet itself is strange enough without adding conspiracy theories on top, and that strangeness, that deviation from what we expect comets to be, is part of why the silence around the spacecraft observations feels so calculated. 3I Atlas was discovered on July 1st, 2025, by the Atlas Survey Telescope in Rio Hurtado, Chile. ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, is a network of robotic telescopes designed to scan the sky every night, looking for asteroids that might pose a threat to Earth. The system is automated. It takes images, compares them to previous images of the same patch of sky, and flags anything that's moved or changed. When something new appears, the software alerts human astronomers, who take a closer look and decide whether it's interesting. On the night of July 1st, Atlas flagged an object moving through the constellation Ophiuchus, fast, too fast to be a main belt asteroid on a normal orbit. When astronomers calculated its trajectory, they realized immediately what they had: an object on a hyperbolic orbit, meaning it wasn't bound to the Sun. It came from interstellar space, it was passing through the solar system, and it would leave, never to return. Within hours, observatories around the world were scrambling to point their telescopes at the newly discovered visitor. Pre-discovery images were found in archives going back to June 14th, which extended the observational baseline and allowed for a more precise orbit determination. By July 3rd, the Minor Planet Center, the official body that catalogues solar system objects, had confirmed the interstellar nature of the object and assigned it the designation 3I Atlas. The 3I means it's the third interstellar object ever confirmed. The Atlas credits the Discovery Survey. And then the real work began. Because finding an interstellar object is one thing, understanding what it is, where it came from, and what it's made of is something else entirely. The first question astronomers wanted to answer was, how big is it? That sounds simple, but it's surprisingly hard to determine. You can't directly measure the size of something millions of kilometers away unless you have a telescope powerful enough to resolve it as more than a point of light. What you can measure is brightness, and from brightness, if you know or can estimate the object's reflectivity, its albedo, you can work backwards to size. But comets complicate things. They're not solid, inert rocks. They're icy bodies that heat up as they approach the Sun, releasing gas and dust that forms a glowing cloud called a coma. That coma makes the comet look much larger and brighter than the nucleus actually is. To estimate the nucleus size, you need to account for how much of the light you're seeing comes from reflected sunlight off the solid surface versus scattered sunlight off the coma dust. NASA's Hubble Space Telescope imaged 3I Atlas on July 21, 2025, when the comet was 277 million miles from Earth. Hubble's incredible resolution revealed a teardrop-shaped coma, a bright core where the nucleus sat, and a faint tail streaming behind. By modelling the coma's brightness and dust production rate, astronomers estimated the nucleus was somewhere between 440 meters and 5.6 kilometers in diameter. That's a huge range, over a factor of 10, which tells you how uncertain the measurement is. But even the lower end of that estimate, 440 meters, is interesting. That's large for an interstellar object. Oumuamua was probably only about 100 meters across. Tyosai-Borisov was estimated at around 500 meters. If 3I Atlas is on the larger end of the range, several kilometers across, that makes it one of the biggest interstellar visitors we've ever seen. Size matters because it relates to mass, and mass determines how the object moves, how it responds to forces like solar radiation pressure and outgassing thrust. If you can measure an object's trajectory precisely enough, you can detect tiny accelerations caused by non-gravitational forces. Those accelerations tell you whether the object is purely passive, being pushed around by sunlight and its own escaping gases, or whether something else is going on. For Oumuamua, that was the key mystery. The object showed a small but measurable acceleration that couldn't be explained by reflected sunlight alone. Comets usually accelerate due to outgassing, the rocket effect when escaping gas pushes on the nucleus, but Oumuamua didn't show signs of a coma or tail, no dust or gas that would produce that thrust. It was, in that sense, anomalous. Avi Loeb, the Harvard astrophysicist, famously suggested that the acceleration could be explained if Oumuamua was a light sail, a thin, artificial structure being pushed by sunlight. Most astronomers disagreed, proposing instead that Oumuamua was outgassing something invisible, like hydrogen, that wouldn't produce a visible coma. For 3I Atlas, the situation is different. The comet clearly has a coma. Hubble saw it. Ground-based telescopes saw it. The object is active, releasing gas and dust as expected for a comet warming up in sunlight. Spectroscopy from NASA's James Webb Space Telescope, captured on August 6, 2025, detected carbon dioxide, water vapor, carbon monoxide, and carbonyl sulfide in the coma. Those are normal cometary volatiles, the kinds of ices you'd expect to find in any comet, interstellar or not. But here's where it gets interesting. The ratios are off. Typical solar system comets have a carbon dioxide to water ratio of about 110 or 120. Water dominates. But early spectroscopic analysis of 3I Atlas showed a CO2-H2O ratio closer to 8:1. There's more carbon dioxide than water, by a lot. That's unusual. It suggests the comet formed in a different chemical environment than solar system comets. Somewhere with more carbon-rich material, somewhere colder, where carbon dioxide could condense into ice before water did. Astronomers have proposed that 3 Atlas formed around a star with low metallicity, meaning fewer heavy elements than our Sun. Low metallicity stars tend to produce carbon-rich protoplanetary disks, the swirling clouds of gas and dust where planets and comets are born. If that's true, and if the comet's trajectory really does trace back to the galactic thick disk, then 3I Atlas could be ancient. Not just billions of years old, but one of the oldest comets we've ever studied, a frozen relic from when the galaxy was young and stars were just beginning to forge heavy elements in their cores. That age estimate, 9 to 13 billion years, is staggering. For context, Earth is 4.5 billion years old. The Sun is 4.6 billion years old. If 3I Atlas really is 10 billion years old, it was already ancient when our solar system formed. It drifted through the galaxy for billions of years, surviving countless close encounters with stars, enduring the radiation of supernova, slowly accumulating a patina of cosmic rays and interstellar dust. And now, by sheer chance, it's passing through our neighborhood, close enough that we can study it. That's why the spacecraft observations matter so much. Earth-based telescopes can measure the comets, brightness and spectrum, but they're limited by distance and atmosphere. Spacecraft, even ones that aren't optimized for comet studies, can get much closer. They can resolve structure in the coma, measure brightness variations that reveal the nucleus's rotation, detect subtle spectral features that ground telescopes might miss. And most importantly, spacecraft can observe the comet when Earth-based telescopes can't, like during the perihelion passage on October 29th, when the comet was on the opposite side of the Sun from Earth. That perihelion, the closest approach to the Sun, was predicted to be the moment of maximum activity. As 3I Atlas reached 1.4 AU, just inside Mars's orbit, solar heating would vaporize ices at the highest rate. The coma would brighten, the tail would lengthen. If the nucleus was going to fragment like Comet 2I Borisov did, perihelion would be when it happened. And the only assets that could observe that critical moment were the spacecraft already in the inner solar system, the Mars orbiters, Parker Solar Probe, and possibly SOHO's coronagraphs. But we're getting ahead of ourselves. Before we talk about what those spacecraft might have seen, we need to establish what we expected them to see, because expectations matter. If the observations match predictions, that's reassuring. If they don't, that's when things get interesting. Based on the spectroscopy and photometry collected during July and August, astronomers modelled 3I Atlas as an active comet with a rotating, irregularly shaped nucleus. The rotation period was uncertain, somewhere between 8 and 24 hours based on light curve variations. The nucleus was ejecting dust and gas from multiple active areas, creating an asymmetric coma that changed over time as different regions rotated into sunlight. As the comet approached perihelion, models predicted it would brighten to around magnitude 12 or 13 at its peak, still too faint to see with the naked eye but easily detectable with small telescopes. The coma would expand, growing from about 25,000 kilometers across in August to perhaps 50,000 or 100,000 kilometers by late October. The dust tail, pushed away from the Sun by radiation pressure, would stretch behind the nucleus, possibly becoming visible in long-exposure photographs. Those predictions were based on the assumption that 3I Atlas was a normal comet, behaving according to the physics we understand. Ices sublimate when heated. Gas expands into space. Dust particles are carried along with the gas, then left behind as the gas dissipates, forming the tail. It's a well-understood process, observed thousands of times in solar system comets. But what if the predictions were wrong? What if 3I Atlas wasn't behaving like a normal comet? What if, during those close encounters with Psyche and the Mars orbiters, the spacecraft detected something unexpected? Let me give you some possibilities, ranging from prosaic to bizarre. Possibility 1. The comet brightened more than expected. Comets can have outbursts, sudden increases in activity when a pocket of volatile ices is exposed, or when part of the surface collapses. If 3I Atlas had an outburst during the spacecraft observation windows, that would be scientifically interesting. It would tell us the nucleus is structurally weak, or that there are volatile reservoirs just below the surface. But it wouldn't be shocking. It wouldn't be something NASA would feel compelled to hide. Possibility 2. The comet fragmented. Interstellar Comet 2I Borisov broke apart during its perihelion passage, probably due to thermal stress from solar heating. If 3I Atlas did the same, and if one of the spacecraft happened to capture images of the fragmentation event, that would be extraordinary. A comet breaking up in real time, especially an ancient interstellar comet, would be a once-in-a-lifetime observation. But again, it wouldn't be secret-worthy. NASA would want to publish that. It would be a triumph for the mission. Possibility 3. The comet's spectrum changed. If the spacecraft spectrometers detected emission or absorption lines that weren't present in earlier ground-based observations that could indicate unusual chemistry or unexpected composition. Maybe the nucleus has layers, different ices at different depths, and as the surface eroded, deeper layers were exposed with different compositions. That would be fascinating, but again, not threatening. It's the kind of discovery that gets written up in Nature or Science, not buried in a classified file. Possibility 4. The comet's trajectory changed. Not by much. We're talking about tiny accelerations, fractions of a millimeter per second squared. But if the spacecraft measured a Doppler shift in the comet's reflected light that didn't match the predicted motion based on solar gravity and normal outgassing, that would be a red flag. It would suggest either an unmodelled force or an error in the mass estimate. Neither is catastrophic, but it would require explanation. Possibility 5. The comet isn't a comet. Stay with me here. I'm not jumping to alien spacecraft. I'm talking about the possibility that 3I Atlas is a different class of object than we've assumed. Maybe it's not primarily ice and rock. Maybe it's metal-rich, a fragment of a destroyed exoplanet's core similar to the asteroid 16 Psyche that NASA's spacecraft is on its way to visit. If spectroscopy revealed strong metallic emission lines, nickel or iron vapor in the coma, that would be bizarre. Comets shouldn't have significant metal content. But fragments of differentiated bodies, worlds that melted and separated into iron cores and rocky mantles before being shattered by collisions, those can be metal-rich. There were early, unconfirmed reports in August 2025 from the Very Large Telescope in Chile that detected nickel in 3I Atlas's coma. Nickel has been seen in other comets before, so it's not unheard of, but the reported abundance was higher than typical. If that detection holds up, and if follow-up observations showed even stronger metal signatures, it would raise questions about the comet's origin. Where do metal-rich comets come from? What kind of planetary system produces them? And if 3I Atlas is from the galactic thick disk, from the era of cosmic noon, does that mean the early galaxy had different planet formation processes than we see today? Those are the questions scientists would want to answer, and answering them requires data, high-resolution images, precise spectra, measurements of the comet's rotation, shape and activity, exactly the kind of data that Psyche, the Mars orbiters, and JUICE were positioned to collect. So, why haven't we seen it? Where's the data? The optimistic answer is that it's coming. Science takes time. Images need to be calibrated, corrected for instrumental effects, processed into usable formats. Spectra need to be analysed, compared to laboratory data and models. Papers need to be written, reviewed, revised and published. Even under normal circumstances, there's a lag between observation and publication, measured in months, sometimes years. The pessimistic answer is that the data showed something unexpected, something that doesn't fit the narrative of a normal comet on a normal trajectory, and that someone, somewhere, made the decision to hold it back. Not forever, necessarily, just long enough to figure out what it means, long enough to decide how to frame it, long enough to ensure that when the public finally learns what the spacecraft saw near 3I Atlas, the story is controlled, managed, sanitized. I don't know which answer is correct, but I know which one the evidence suggests, and in the next part we're going to walk through that evidence piece by piece, starting with the spacecraft that was supposed to be humanity's best observer during the critical perihelion passage, and the government shutdown that made sure we'd never hear what it found. October 1st, 2025, midnight Eastern Time, the United States federal government shuts down. Not with drama, not with emergency declarations, just the quiet expiration of a continuing resolution that Congress failed to renew. Funding lapses. Federal agencies enter their continuity plans. Non-essential employees are furloughed. Government websites display notices. Due to a lapse in appropriations, this agency is closed. It's not unprecedented. It happens every few years when budget negotiations break down. The shutdowns usually last days, sometimes weeks. In 2018-2019, the government was closed for 35 days, the longest shutdown in US history. Federal workers go without paychecks. National parks close. Services are suspended. But the essential functions continue. Air traffic control, border security, emergency services, and crucially for our story, space missions. NASA's continuity plan, the document that outlines which activities continue during a funding lapse and which don't, is public. You can read it yourself, it's dry. Bureaucratic prose, but it's precise. The plan states that NASA will maintain space satellite operations when necessary to protect life and property. That includes the International Space Station, definitely. Crew safety is paramount. It includes Earth observation satellites that monitor weather and climate, because their data feeds into emergency response systems. And it includes deep space missions, because letting a spacecraft drift off course or lose power would mean losing $1 billion asset. So when the government shut down on October 1st, the Mars Reconnaissance Orbiter kept flying. The flight control team at the Jet Propulsion Laboratory kept working, though whether they were being paid is a different question. Commands were sent. Telemetry was received. The spacecraft's health was monitored. If MRO needed a thruster burn to adjust its orbit or reorient its antenna, that would happen. The mission, in operational terms, continued. What didn't continue was public communication. NASA's Public Affairs Office was furloughed. The people whose job is to write press releases, update mission websites, post images to social media, answer questions from journalists, they all went home. The flow of information from NASA to the public which under normal circumstances is a steady stream of updates and discoveries and beautiful images, stopped completely. Here's the exact language from the continuity plan on page 12. Citizens will not have access to NASA.gov or other NASA public websites during a lapse in appropriations. Social media accounts will not be updated. Press releases will not be issued. It goes on to say that mission-critical data will be archived, but public release of that data is considered a non-essential activity. Now, think about the timing. On October 1st, the shutdown begins. On October 3rd, Through-Eye Atlas passes within 29 million kilometers of Mars, the closest it will come to any planet during its journey through the solar system. The Mars orbiters have the best viewing geometry they'll ever have. The comet is active, bright, observable with their instruments, and the public affairs machinery that would normally announce and celebrate this observation is offline. Coincidence? Let's examine that claim carefully. The shutdown wasn't a surprise. These things don't happen overnight. Congressional budget negotiations had been deteriorating for weeks. By mid-September, it was clear that a continuing resolution would be needed to keep the government funded past the end of the fiscal year on September 30th, and by September 25th, it was obvious that resolution wasn't going to pass. Federal agencies had days of warning. NASA had days of warning, which means NASA knew, going into the last week of September, that on October 1st their public communications would go dark. They knew that on October 3rd, during the Mars observation window for 3-Eye Atlas, there would be no press releases, no website updates, no way to tell the public what was being observed. Did they try to get ahead of it? Did they issue press releases on September 28th or 29th, pre-announcing the observations and promising that data would be released after the shutdown ended? They did not. The last NASA press release mentioning 3-Eye Atlas was dated August 25th, when they announced Webb telescope results showing carbon dioxide in the comet's coma. After that, silence. The European Space Agency, by contrast, was perfectly transparent. On September 28th, ESA published a press release stating that Mars Express and ExoMars Trace Gas Orbiter would observe 3-Eye Atlas during October 1st through 7th. They explained the geometry, the instruments that would be used, and what they hoped to learn. ESA scientists gave interviews. On October 8th, after the observations were complete, ESA released images. Fuzzy, low-resolution shots of a white dot moving against a black background, but images nonetheless. They showed the world what they'd seen. NASA showed nothing. Now, you might argue that NASA couldn't release images during a shutdown, that's true, but they could have issued a pre-shutdown press release stating their intentions. They could have explained that MRO and other assets would be observing 3-Eye Atlas, and that results would follow once funding was restored. Instead, they went silent before the shutdown even began. That's not standard procedure. NASA loves talking about their missions. They love celebrating observations and discoveries. When something interesting is about to happen, they hype it up. Press kits are prepared, media briefings are scheduled, social media campaigns are planned. The fact that none of that happened for the 3-Eye Atlas observations, that NASA entered the October window without public acknowledgement, suggests either profound incompetence or deliberate choice. Let me lay out what we know happened on the NASA side during early October, based on fragmentary evidence from mission logs, academic papers, and careful reading between the lines. Mars Reconnaissance Orbiter, or MRO, is equipped with HiRISE, the High-Resolution Imaging Science Experiment. It's a half-meter reflecting telescope, one of the most powerful cameras ever sent to another planet. HiRISE is designed to photograph the Martian surface at resolutions down to 30 centimeters per pixel. From Mars orbit, it can read the serial numbers on defunct landers. But on October 3rd, 3 Atlas wasn't on the Martian surface. It was 29 million kilometers away. At that distance, HiRISE's resolution drops to about 30 kilometers per pixel. You're not going to see surface features on the comet's nucleus, which is probably only a few kilometers across at most. What you could see is the coma, the glowing cloud of dust and gas. You could measure brightness variations, detect asymmetries, watch for jets or outbursts, and most importantly, you could measure the comet's position very precisely, which feeds into orbital calculations and can reveal non-gravitational accelerations. According to the academic paper published by Marshall Eubanks and colleagues in August, MRO was expected to observe 3-Eye Atlas during the close approach. The observation was feasible, the geometry was favourable, the science return was high, The paper even included tables showing the predicted brightness, angular size and motion of the comet as seen from MRO's orbit. So did MRO observe? The publicly available MRO image archive, hosted on the planetary data system, shows a gap. No high-rise images from October 3rd, no context camera images, no spectrometer data from that date has been released. There are images from October 1st, there are images from October 5th. But October 3rd, the day of closest approach, is blank. Maybe HiRISE wasn't tasked to observe the comet. Maybe the observation was attempted but failed due to technical issues. Maybe the data exists but hasn't been released yet due to processing delays. Or maybe the data was classified the moment it came down from orbit, flagged by automated systems or human reviewers who saw something in those pixels that didn't fit the expected profile. I want to stress that I'm speculating here. I don't have inside information. I don't have leaked documents or whistleblower testimony. What I have is a gap in the public record during a window when observations were expected, combined with a government shutdown that provided perfect cover for that gap. But MRO wasn't the only asset at Mars. There's also MAVEN, the Mars Atmosphere and Volatile Evolution mission. MAVEN isn't designed to image comets. Its instruments are optimized for studying the Martian upper atmosphere and the solar wind. But MAVEN does carry a magnetometer and particle detectors. If 3I Atlas had an unusually strong magnetic field, or if it was shedding charged particles in unexpected ways, MAVEN might have detected it. Comets don't typically have strong intrinsic magnetic fields. They're not large enough or dense enough to generate a dynamo like Earth does. But comets do interact with the solar wind, the stream of charged particles flowing from the sun. When the solar wind hits a comet's coma, it creates a bow shock and a magnetotail. MAVEN could potentially detect perturbations in the solar wind caused by the comet's presence, even at 29 million kilometers. Has MAVEN reported any anomalous readings from early October? Not publicly. The mission's data archive shows routine measurements of solar wind density, magnetic field strength, and particle fluxes. If there were any spikes or anomalies coinciding with the 3I Atlas flyby, they're not jumping out of the publicly available data. But then, anomalies wouldn't necessarily be obvious without careful analysis and comparison to baseline conditions. Then there's Tianwen-1, China's Mars orbiter. Tianwen-1 carries high-resolution cameras comparable to HiRISE. The spacecraft is capable of observing 3I Atlas, but China's space program is less transparent than NASA or ESA. They release images selectively, often weeks or months after they're taken. They don't maintain public data archives with the same accessibility as Western agencies. So even if Tianwen-1 observed the comet, we might not hear about it for a long time, if ever. The lack of data from Tianwen-1 isn't surprising. What is surprising is the lack of data from NASA, an agency that prides itself on openness and public engagement. And what makes it even more suspicious is that the shutdown provided such convenient cover. During a normal operational period, if MRO observed something unusual and decided not to release the images immediately, people would ask questions. Journalists would file Freedom of Information Act requests. Scientists would complain at conferences. But during a shutdown, everyone assumes the delay is bureaucratic. It's expected. It's normal. By the time the shutdown ended on October 15th, 2 weeks had passed since the observations. 2 weeks for the data to be reviewed, analysed, and, if necessary, reclassified. 2 weeks for decisions to be made about what could be released and what couldn't. And when NASA's website finally came back online, when the Public Affairs Office returned to work, the focus was on restoring normal operations, catching up on backlogged announcements, getting missions back to regular communication cadence. The October 3rd observations of 3I Atlas. They fell through the cracks. Or they were pushed through the cracks. It's hard to tell the difference from the outside. Now let's talk about what the Mars orbiters should have seen if 3I Atlas was behaving like a normal comet. Based on models and ground-based observations from August and September, astronomers predicted the comet would be around magnitude 12 to 13 as seen from Mars on October 3rd. That's faint, but well within the detection capabilities of HiRISE or similar instruments. The coma would span tens of thousands of kilometers, appearing as a diffuse glow with a brighter core where the nucleus sits. If the comet was actively outgassing, there might be visible jets, localized streams of gas and dust erupting from active areas on the nucleus. These jets would appear as bright rays or fans extending from the core, often changing as the nucleus rotates and different areas come into sunlight. Watching those jets evolve over hours or days would tell you about the nucleus's rotation rate and the distribution of volatile ices on its surface. The dust tail, pushed away from the sun by radiation pressure, should be visible extending behind the nucleus. The tail's shape and brightness would depend on how much dust the comet was producing. More active comets have brighter, longer tails. If the comet had recently had an outburst, the tail might show distinct streamers or knots where clumps of dust were released. All of this is standard cometary behaviour. If that's what the Mars orbiters saw, it would be interesting, it would be worth studying, but it wouldn't be alarming. It wouldn't trigger secrecy. But what if they saw something else? What if, when HIRAS pointed at the predicted location of 3I Atlas, the image showed not one bright core but multiple? What if the comet had fragmented, broken into pieces that were separating as they tumbled through space? Comet fragmentation is rare but not unheard of. It usually happens due to rotational instability or thermal stress. If 3I Atlas fragmented, each piece would have its own coma, its own tail, creating a complex structure that would be fascinating to analyse. Or what if the coma wasn't symmetric? Comets are usually brightest on the sunward side, where solar heating drives out gassing. But what if 3I Atlas showed unexpected brightness variations, bright spots that didn't correlate with solar illumination? That could indicate localized activity from subsurface pockets of volatiles. Or it could indicate something else, something reflecting light in ways that natural surfaces shouldn't. Or what if the comet's motion didn't match the predicted trajectory? Astrometry, precise position measurement, is one of the things spacecraft do very well. By comparing the observed position of the comet to its predicted position based on gravitational models, you can detect tiny accelerations. If the comet was accelerating more or less than expected from normal outgassing, that would be a red flag. It would mean either the mass estimate was wrong, or the outgassing model was wrong, or there was a third option no one wanted to say out loud. Let me give you a concrete example of why this matters. When Oumuamua showed its anomalous acceleration in 2018, the astronomy community split into camps. Some scientists proposed that the object was outgassing hydrogen, which would be invisible but could produce thrust. Others, notably Avi Loeb, suggested the acceleration was consistent with a light sail, a thin artificial structure being pushed by solar radiation. The debate became heated, with accusations of sensationalism and closed-mindedness flying in both directions. The reason the debate was so intense is that the stakes were so high. If Oumuamua was natural, it taught us that comets can behave in unexpected ways, that our models need refinement. But if it was artificial, if it really was a probe from another civilization, that would be the most important discovery in human history. The fact that we couldn't get better data, that Oumuamua left the solar system before we could send a spacecraft to intercept it, left the question forever unresolved. With 3I Atlas, we had a second chance. This time, we had months of warning. This time, we had spacecraft already in position. This time, we could get close-up observations during the critical perihelion passage, when the comet was most active and most likely to reveal its true nature. And then, just as that critical window opened, the machinery of public disclosure shut down. I'm not saying that's proof of anything, but it's suspicious. And suspicion is what keeps you awake at night, turning over questions that don't have comfortable answers. Let's move forward to the next checkpoint, the JUICE observation scheduled for November 4th. Because if the pattern holds, if there's something about 3I Atlas that's being kept quiet, JUICE's observation should also disappear into silence. And if they don't, if ESA releases data showing a normal comet behaving normally, that tells us something too. It tells us the problem, if there is one, is specifically with NASA's data. Which raises a whole other set of questions about what makes NASA's observations different. But before we get there, we need to talk about what happened on October 29th, the day of perihelion, when 3I Atlas reached its closest point to the Sun, because that's when the comet should have been most active, most visible, and most likely to do something unexpected. And as it turns out, there were eyes watching. Not spacecraft exactly, but something almost as good. The solar observatories that monitor the Sun's corona, looking for coronal mass ejections and other space weather events. SOHO, the Solar and Heliospheric Observatory, is a joint ESA-NASA mission that's been watching the Sun since 1995. One of its instruments, LASCO, is a coronagraph, a device that blocks the Sun's bright disk so you can see the faint corona around it. LASCO has accidentally discovered thousands of comets over the years, small icy bodies that pass close to the Sun and briefly appear in the coronagraph's field of view before they're vaporized or flung back into space. 3 Atlas's trajectory brought it within LASCO's field of view around October 28th through 30th. If the comet was bright enough and active enough, LASCO would see it. And unlike NASA's mission-specific websites that went dark during the shutdown, SOHO's data feed is automatic. Images are posted in near real time within hours of being taken. You can browse the archive yourself day by day and see what LASCO saw. On October 29th, 2025, LASCO imaged the Sun's corona as usual. The images are publicly available. You can look at them right now. And in those images, if you know where to look, if you zoom in and adjust the contrast, there's a faint smudge, a streak of light moving against the background stars exactly where 3I Atlas was predicted to be. So LASCO did see the comet. That's confirmed. The comet survived perihelion. It didn't fragment catastrophically. It didn't vaporize. It passed through its closest approach to the Sun and emerged on the other side, still intact, still active. But here's what's strange. The brightness in the LASCO images is lower than expected. Not dramatically lower, but noticeably. Based on the activity levels observed in August and September, astronomers predicted the comet would reach magnitude 11 or 12 at perihelion. That's bright enough to be easily visible in LASCO's images, a clear bright point that stands out against the background. But the actual brightness appears closer to magnitude 13 or 14, several times fainter than predicted. Why would the comet be dimmer than expected? There are several possible explanations. Maybe the nucleus is smaller than estimated, so there's less surface area to produce gas and dust. Maybe the volatiles are more deeply buried, covered by a layer of dark, non-volatile crust that insulates the ice below. Maybe the comet had already shed most of its easily released material during previous perihelion passages, if it's been looping around other stars for billions of years. Or maybe the comet isn't what we think it is. Maybe it's not primarily ice. Maybe it's rock or metal, with only a thin veneer of volatiles. That would explain the low activity level. It would also match the suspected nickel detection from August, but it would be deeply weird. Metal-rich comets from interstellar space are not something our models predict. The LASCO images don't have the resolution to answer these questions. They show that the comet exists, that it's where it's supposed to be, and that it's fainter than expected. That's tantalizing but not conclusive. What we need is high-resolution spectroscopy, detailed photometry, images that can resolve the coma structure, exactly the kind of data that spacecraft can provide. Which brings us back to the central mystery. If the Mars orbiters observed the comet on October 3rd, and if those observations showed something unusual, low activity, unexpected spectral features, evidence of fragmentation, NASA would have a choice. They could release the data immediately, sparking questions and speculation. Or they could hold it back, classify it, or embargo it, and take time to figure out what they're looking at before going public. The shutdown gave them that time. 14 days of bureaucratic cover while they decided how to handle it. And when the shutdown ended, when NASA returned to normal operations, the decision had apparently been made. Say nothing. Release nothing. Let the October observations fade into the background. Just another data set sitting in an archive somewhere, waiting for some graduate student to stumble across it years from now and ask why it was never published. That's the optimistic interpretation. The pessimistic interpretation is that the data won't ever be published, that it's been classified under some national security justification, maybe related to space domain awareness or asset protection, that what the spacecraft saw near 3I Atlas is now locked in a server room at Fort Meade or in a skiff at NASA headquarters, accessible only to people with the right clearances and a need to know. I don't have evidence for the pessimistic interpretation, but I don't have evidence against it either. And in the absence of evidence, in the silence that followed the October observations, speculation grows like mold in a dark room. So let's do what investigators do. Let's look at the patterns. Let's map the timeline. Let's identify who had opportunities to observe what they should have seen and what we actually know they reported. And then, when we lay it all out, when we see the full picture, we'll ask the question that matters. Is this silence normal, or is someone keeping a secret? November 4th, 2025. While NASA's silence about the October observations continues, the European Space Agency's Jupiter Icy Moons Explorer JUICE reaches its own observation window for 3I Atlas. The spacecraft is 64 million kilometers from the comet, farther than Psyche was, farther than the Mars orbiters, but still close enough that JUICE's instruments should be able to gather valuable data. JUICE is in an interesting position in the solar system right now. The spacecraft launched in April 2023, beginning a complex 8-year journey to Jupiter. But it can't fly there directly. Jupiter is too far, the spacecraft too heavy, and the fuel too limited. Instead, JUICE is taking the scenic route, executing a series of gravity assists that will slingshot it across the solar system, building up speed with each planetary encounter. On August 31, 2025, JUICE completed a Venus flyby, skimming just 6,800 kilometers above the planet's cloud tops. That encounter bent the spacecraft's trajectory and added velocity, sending it on a path that will eventually bring it back to Earth for 2 more gravity assists before finally heading outward to Jupiter. But during November 2025, JUICE is in the inner solar system, coasting between Venus and Earth, with relatively little happening from a mission operations perspective, which makes it the perfect time to point the cameras at a passing interstellar comet. JUICE carries 2 main imaging systems. There's JANUS, the Jovis Amora Machinatorum Undique Scrutator, which is Latin for comprehensive examination of Jupiter and its moons, because European space scientists love their classical references. JANUS is a visible light camera designed to map the surfaces of Jupiter's icy moons, with resolutions down to a few meters per pixel when in orbit. At 64 million kilometers from 3I Atlas, JANUS won't see that kind of detail, but it can measure brightness, detect the coma, maybe resolve some structure if the comet is active enough. Then there's MAGIS, the Moon's and Jupiter Imaging Spectrometer, which operates in infrared wavelengths. MAGIS can detect heat signatures and identify chemical compositions based on spectral absorption features. If 3I Atlas is releasing unusual volatiles, molecules not typically seen in comets, MAGIS might catch them. And crucially, MAGIS can observe at wavelengths where certain materials, like metals or organic compounds, have distinctive signatures. According to the observation plan discussed in academic papers and ESA press materials, JUICE would attempt observations during a window spanning November 2nd through November 25th. The closest approach, when the geometry was optimal, occurred on November 4th. After that, the comet would continue moving, away, fading as it receded from both the Sun and the spacecraft. So what did JUICE see? As of mid-November 2025, we're waiting. ESA has stated publicly that data from JUICE's observations won't be downlinked until February 2026. That's not unusual. JUICE is far from Earth right now, on the opposite side of the Sun from our planet's perspective, which limits communication bandwidth. The spacecraft is using its medium-gain antenna instead of its high-gain antenna because the high-gain dish is being used as a heat shield, protecting sensitive instruments from solar radiation. Data transmission rates are slow, measured in kilobits per second, rather than the megabits or gigabits that closer spacecraft can achieve. Additionally, JUICE's onboard storage is limited. The spacecraft prioritizes essential housekeeping data, information about its own health and status, over science data. Science observations get recorded to solid-state memory and queued for transmission when bandwidth is available. If there's a lot of data, from multiple instruments observing over multiple days, it can take weeks or months to downlink everything. So the February 2026 timeline is plausible. It's not inherently suspicious. ESA is being transparent about why the data is delayed and when they expect to release it. That's very different from NASA's approach with the September and October observations, where there was no advance notice, no explanation, just silence. But here's what makes the JUICE situation interesting. If ESA releases data in February 2026, showing that 3I Atlas looked perfectly normal, that it was behaving like a standard comet with expected brightness and spectral features, that will tell us something important. It will tell us that whatever NASA saw or didn't see in September and October was either unique to those observation geometries, or was misinterpreted or was classified for reasons unrelated to the comet's actual properties. On the other hand, if ESA's data also shows anomalies, if JUICE detected unexpected spectral lines, or brightness variations or structural features that don't match a normal comet, then we'll know the issue isn't observer-dependent. The anomaly, if there is one, is real and measurable by independent parties, and if ESA delays beyond February, or if the data when released is incomplete or heavily processed or lacks the raw observations that scientists typically share, that will be its own kind of answer. It will suggest that ESA is under pressure, either from NASA or from European government agencies, to coordinate their messaging about 3I Atlas. International space cooperation is a beautiful thing when it works. Agencies share data, collaborate on missions, support each other's exploration goals, but cooperation also creates dependencies. NASA provides deep space communication support for many ESA missions. American tracking stations, part of the Deep Space Network, are sometimes the only antennas that can reach a distant spacecraft. If NASA wanted to exert pressure on ESA to withhold or delay data, they have leverage. I'm not saying that's happening, I'm saying it's possible, and in the absence of transparency, possibilities multiply. Let's talk about what else was watching during November. Because JUICE wasn't the only set of eyes potentially pointed at 3I Atlas during the post-perihelion period. Parker Solar Probe, NASA's spacecraft studying the Sun's corona, was in the vicinity during late October and early November. Parker's orbit takes it on close passes around the Sun, diving through the corona to measure magnetic fields, plasma properties, and solar wind. The spacecraft's WHISPER instrument, the Wide Field Imager for Solar Probe, is essentially a pair of cameras designed to photograph the solar wind and any comets or asteroids that happen to pass through the field of view. Parker has discovered several comets incidentally over its mission, small sun-grazing objects that weren't known before Parker saw them. Could WHISPER have captured 3I Atlas? In principle, yes. The comet's perihelion put it within WHISPER's potential field of view during late October. If Parker's cameras were pointed in the right direction at the right time, they could have imaged the comet. But Parker operates under different constraints than a normal imaging mission. The spacecraft spends most of its time with its heat shield pointed directly at the Sun, protecting the instruments from temperatures that would melt steel. When WHISPER is active, it's photographing material near the Sun, which means looking at regions of extremely high background light. Detecting a faint comet against that glare is challenging. Additionally, Parker's data downlink is limited. The spacecraft collects far more data than it can transmit, so mission planners prioritize what gets sent back to Earth. Solar science data takes precedence. Incidental observations of comets might not make the cut, especially if the comet wasn't pre-identified as a target of interest. So it's entirely possible that Parker imaged 3I Atlas, and we'll never know because the data was deprioritized and eventually overwritten when the spacecraft's storage filled up. Or maybe Parker didn't see the comet at all because WHISPER wasn't pointed in the right direction. Without access to Parker's observation logs, which aren't public, we can't know for sure. Then there's Europa Clipper, NASA's mission to Jupiter's moon Europa, which launched in October 2024. Clipper's on a trajectory similar to JUICE, using gravity assist to reach the outer solar system. According to orbital mechanics calculations, Clipper's path brought it relatively close to 3I Atlas's orbit in late October, possibly close enough that the spacecraft could have passed through the comet's dust tail. Passing through a comet's tail would be an extraordinary opportunity. The tail is made of dust particles shed by the nucleus, ranging in size from micrometers to millimeters. These particles drift along the comet's orbit, gradually spreading out due to radiation pressure and gravitational perturbations. A spacecraft flying through the tail wouldn't necessarily collide with dust. The particle density is extremely low, but sensitive instruments might detect individual impacts or measure scattered sunlight off the grains. Europa Clipper carries a dust analyzer, an instrument designed to study particles in Jupiter's environment. If the spacecraft flew through 3I Atlas's tail and detected dust grains of interstellar origin, that would be scientifically priceless. Each grain would carry isotopic and chemical signatures from the comet's formation environment, a direct sample of material from another star system. But there's been no announcement from NASA about any such detection. No press release, no paper, no data release. Maybe Clipper didn't pass through the tail after all. Maybe the geometry didn't work out. Or maybe the dust analyzer did record impacts, and that data is sitting in a queue somewhere, waiting to be analysed by scientists who are focused on preparing for the Jupiter arrival years from now and haven't prioritised the comet encounter. Or maybe, once again, the data was flagged as interesting enough to require review before public release, and it's trapped in the same bureaucratic or classification limbo as the Psyche and Mars orbiter observations. I want to pause here and address something directly. Some of you listening might be thinking, this is just normal science operations. Data takes time to process. Missions have priorities. There's no conspiracy here, just the slow grind of bureaucracy and limited resources. And you might be right. In fact, statistically, you're probably right. The most likely explanation for the silence around 3I Atlas observations is boring. It's budget constraints and shutdown disruptions and scientists who are overworked and understaffed trying to do their best with limited time. But here's the thing about patterns. When you see one anomaly, one data gap, one delayed release, you shrug it off. When you see two, you start to wonder. When you see three or four, all clustered around the same event, all involving the same target, all happening during a period when normal communication channels were disrupted, you don't get to call it coincidence anymore. You have to at least consider that it might be coordination. And if it is coordination, if there's a deliberate effort to control information about 3I Atlas observations that raises the biggest question of all, why? What could a comet, even an interstellar one, possibly show that would justify secrecy? Let me walk you through some scenarios, from least to most unsettling. Scenario 1. 3I Atlas is a normal comet, but its composition is unusual enough to rewrite textbooks about planetary formation in the early galaxy. Maybe the carbon dioxide to water ratio is even more extreme than early measurements suggested. Maybe there are complex organic, molecules, prebiotic chemistry that raises questions about how common life's building blocks are in the universe. That's scientifically important, but it's not threatening. Scientists would want to publish that, not hide it. Scenario 2. The comet fragmented in an unusual way, breaking into pieces that showed clear internal structure. Maybe the nucleus wasn't homogeneous. Maybe there were distinct layers, or voids, or density variations that suggest a formation process we don't understand. Interesting, but again, not secret-worthy. Scenario 3. The comet's trajectory showed non-gravitational acceleration that can't be explained by normal outgassing. Maybe the magnitude or direction of the acceleration doesn't match any cometary activity models. Maybe repeated observations from different spacecraft all measured the same anomalous motion, ruling out instrumental error. That would be troubling because it would mean either our physics is wrong or there's an unmodelled force acting on the object. But even that, as strange as it would be, wouldn't necessarily trigger classification. It would trigger intense scientific interest and debate. Scenario 4. The comet's surface or coma showed structures that appeared artificial or organised. Not random jets and dust clouds, but geometric patterns, straight lines, angular features, things that don't occur naturally. This is where we start entering territory that would genuinely alarm people. Because if you rule out natural explanations, you're left with unnatural ones. And unnatural, in the context of an interstellar object, means one thing: technology. I'm not endorsing scenario 4. I'm not claiming it's true. But I am pointing out that if any spacecraft imaged something like that, even ambiguously, even with low resolution and high noise, the reaction wouldn't be to immediately publish. The reaction would be to classify, to restrict access, to bring in experts from defense and intelligence communities, and to very carefully decide what to tell the public and when. That's not paranoia, that's policy. The United States has protocols for handling potential evidence of extraterrestrial intelligence. Those protocols are classified, but we know they exist because of oblique references in government documents and testimony from people who've been involved in related programs. If a NASA spacecraft stumbled across something that even remotely suggested artificiality, those protocols would activate. Now, here's where the European contradiction comes in. ESA isn't bound by US classification policy. They're independent. If their spacecraft saw something extraordinary, they'd be under no legal obligation to keep it secret. ESA member states have their own national security concerns, of course, but the agency as a whole has a strong culture of scientific openness. They share data, they publish findings, they engage with the public. So if JUICE observes 3I Atlas in November and detects the same anomalies that hypothetically triggered NASA's silence, ESA would face a choice. Do they publish, potentially contradicting or undercutting NASA's position? Do they coordinate with NASA, agreeing to withhold or delay information in the interest of allied cooperation? Or do they split the difference, releasing some data while holding back the most sensitive findings? The answer to that question will tell us a lot about what's really going on. If ESA releases everything in February 2026, raw images, calibrated spectra, full observation logs, and it all shows a normal comet, then we can reasonably conclude NASA's silence was just bad timing and bureaucratic dysfunction. But if ESA's release is delayed, incomplete, or coordinated with a simultaneous NASA announcement, that's a different story. That suggests the agencies are managing a narrative together, and if ESA publishes data that contradicts the normal comet hypothesis, that shows anomalies, unusual features, unexplained observations, and NASA still says nothing, that would be the most damning outcome. It would prove that NASA has data they're choosing not to share, even when independent confirmation exists. We won't know which scenario plays out until February 2026 at the earliest. But we can watch for signals in the meantime. We can track whether ESA officials give interviews about JUICE's observations. We can monitor academic conferences where preliminary results might be presented. We can watch for preprint papers on RCIV discussing the comet's properties based on spacecraft data. And most importantly, we can watch to see if anyone asks the question publicly. If journalists start pressing NASA for information about the September and October observations, if members of Congress, who have oversight of NASA's budget, demand answers about what the spacecraft saw, if scientists, frustrated by the lack of data releases, start speaking out at conferences or on social media, silence is only sustainable when people accept it. The moment someone with credibility and platform starts asking uncomfortable questions, the silence becomes untenable. Either NASA provides answers, or the questions multiply. Which brings us to the next layer of this story. Because it's not just about what the spacecraft saw, it's about who else was watching, using assets we don't normally think about when we talk about space exploration. It's about the black budget observers, the classified satellites and ground-based systems that track everything in Earth orbit and beyond. They don't publish their data, they don't hold press conferences, but they see things, and sometimes what they see leaks. Let me tell you about the infrastructure nobody discusses when we talk about space exploration. The telescopes that don't appear in NASA press releases, the tracking stations that aren't listed on public websites, the data streams that flow into buildings with no windows and servers that aren't connected to the internet. The United States operates a space surveillance network, a collection of ground-based radars and optical telescopes dedicated to tracking every object in Earth orbit and many objects beyond. This network is run by the US Space Force, the military branch created in 2019 specifically to handle space domain awareness and defense. The network's primary mission is to catalog satellites, debris, and potential threats, maintaining a database of everything from active communication satellites to paint flecks floating in orbit. But the capabilities extend far beyond Earth orbit. Some of the optical telescopes in the network can track objects in cislunar space, the region between Earth and the Moon. They can detect satellites in highly elliptical orbits. They can watch spacecraft on interplanetary trajectories. And while the system isn't optimized for deep space observation, isn't designed to track comets millions of kilometers away, there are specific assets within the network that could, in principle, observe something like 3i Atlas if tasked to do so. Let me give you an example. The Space Surveillance Telescope, or SST, is a ground-based optical telescope operated by the Space Force. It's located in Australia, providing coverage of the Southern Hemisphere sky. SST was originally built for the Defense Advanced Research Projects Agency, DARPA, as a technology demonstrator for wide-field space tracking. The telescope has a 3.5-meter primary mirror and a field of view spanning 3.5 square degrees, enormous by astronomical standards. SST's purpose is to find and track satellites and debris, but the optics are good enough to detect objects much fainter and more distant than typical space debris. In asteroid surveys, similar telescopes have detected objects at the edge of the solar system, trans-Neptunian objects billions of kilometers away. If SST or another military space surveillance telescope was pointed at 3i Atlas during September, October, or November, it could have collected images and photometry that rivaled or exceeded what civilian observatories managed. Would the Space Force task a surveillance telescope to observe an interstellar comet? On the surface, it seems unlikely. Military assets have military missions. They're not supposed to be used for scientific research unless there's a clear defense or national security justification. But here's the thing. Space Force's mission includes detecting and characterizing objects that could pose a threat to US space assets. That mission is broad. It includes monitoring for anti-satellite weapons, tracking foreign satellites capable of inspection or interference, and identifying anomalous behaviour that might indicate hostile intent. An interstellar object passing through the solar system, especially one that attracted significant attention from civilian space agencies, could reasonably fall under that mandate. Not because anyone seriously believes 3i Atlas is a weapon, but because the object represents an unknown, and unknowns are threat assessed until proven benign. Additionally, observing 3i Atlas would be a useful exercise for the surveillance network. It would test the system's ability to detect and track fast-moving objects on hyperbolic trajectories. It would provide calibration data, a known target with predictable motion that can be used to validate tracking algorithms and sensor performance. Space Force could justify the observation as a training opportunity, using the Comet as a proxy for tracking more sensitive targets. So the question isn't whether Space Force could observe 3i Atlas. The question is whether they did, and if so, what they saw. There's no public record of Space Force observations. That's not surprising. Military space surveillance data is classified by default. Orbital elements for satellites are published through a public catalogue called SpaceTrack, but only for unclassified objects. Classified satellites, reconnaissance assets, signals intelligence platforms, those don't appear in the catalogue, and data from surveillance telescopes observing anything beyond Earth orbit wouldn't appear either. But information leaks. It always does. People talk, analysts mention things to colleagues, reports circulate within the defense community, and sometimes through FOIA requests or journalistic investigation, or just plain gossip, pieces of information make their way into public domain. In mid-October 2025, there were posts on astronomy forums from users claiming insider knowledge. Anonymous accounts, no verification, the kind of thing you'd normally dismiss as LARPing or attention-seeking. But some of the details were oddly specific. One post claimed that non-NASA assets had imaged 3i Atlas during perihelion, and that the thermal signature was inconsistent with predicted activity levels. Another mentioned spectral anomalies in the near-infrared that don't match cometary profiles. These posts were quickly deleted. The accounts that made them went silent. That could mean the posts were fake and the users got bored, or it could mean someone noticed and applied pressure to shut down the leaks. I want to stress that I can't verify any of this. I'm reporting what circulated online, not endorsing its accuracy. But the pattern is interesting. Rumours about anomalous observations, specifically mentioning military or classified assets, appearing briefly and then being scrubbed. It fits a profile. Now let's talk about ground-based telescopes outside the military network. There are dozens of professional observatories and hundreds of amateur astronomers who observed 3i Atlas during its pass through the inner solar system. These observers have no obligation to coordinate with NASA or classify their findings. If they saw something unusual, they could publish it. Some did. There are light curves, plots of the comet's brightness over time, posted on amateur astronomy websites and forums. The curves show the expected trend, brightening as the comet approached perihelion, then fading as it receded. But there are wiggles in the curves, short-term variations that suggest rotation or changing activity levels. Nothing dramatic, but not perfectly smooth either. Some observers noted colour variations. The comet appeared slightly redder in some observations, bluer in others. That could indicate changing dust properties, different grain sizes or compositions being released at different times. Or it could be measurement noise, instrumental artifacts, atmospheric effects. Without careful calibration and comparison between observers, it's hard to say. What's missing from the amateur data is high-resolution spectroscopy. That requires large telescopes and sensitive spectrographs, equipment that's beyond the reach of amateurs and even many professional observatories. The best spectra of 3i Atlas came from Hubble, Webb, and large ground-based telescopes like the Very Large Telescope in Chile and the Keck Observatory in Hawaii. Those observations, the ones that showed carbon dioxide, water vapour, cyanide, and possibly nickel, were published in press releases and preprint papers. They're part of the public record. But those observations mostly happened in July and August, before the comet became difficult to observe from Earth due to its proximity to the Sun. The observations that matter, the ones from late September through November, when the comet was most active and when spacecraft had the best views, those haven't been published. Or if they have, they're buried in data archives that require specialised knowledge to access and interpret. Let me walk you through what it would take for you, a motivated individual, to find this data yourself. Because one of the principles of open science is that data should be accessible. If it's truly public, you should be able to get it. For NASA missions, data is archived in the Planetary Data System, or PDS. The PDS is a collection of online repositories organized by mission and instrument. If you want to see images from Mars Reconnaissance Orbiter's HiRISE camera, you go to the HiRISE PDS node, search by date or target, and download the files. The files are in FITS format, Flexible Image Transport System, a standard used in astronomy. You need specialized software to open and view FITS files, but the software is free and the process is well documented. So if you wanted to check whether HiRISE observed 3I Atlas on October 3rd, you'd go to the HiRISE PDS archive, search for observations from that date, and see what comes up. If there's a data gap, no observations listed, that's your first clue that either the observation didn't happen or the data hasn't been released. I walked through this process myself. As of mid-November 2025, the HiRISE archive shows observations from October 1st and October 5th. October 3rd is missing. Not listed as observation attempted but failed. Not listed as data being processed. Just absent from the catalogue. That absence is meaningful. HiRISE takes images, constantly. The camera is always pointed at Mars, always collecting data. The only way you don't get observations on a given date is if the spacecraft was in safe mode, if the instrument was powered off for maintenance, or if someone decided not to archive the data. Safe mode events are publicly reported. Instrument maintenance schedules are published. So if October 3rd was a normal operational day, and the archive is still empty months later, the most likely explanation is that data exists but hasn't been released. Now, it's possible the data is embargoed. Some missions have proprietary periods where the science team gets exclusive access for a set amount of time before making data public. But MRO has been operating since 2006. Most of its data releases are routine and timely. A multi-month embargo for a target of opportunity observation would be unusual. For Psyche, the situation is even murkier. The spacecraft is so new, launched in 2023, that its data release cadence isn't fully established. There's a mission website with some images and updates, but no comprehensive archive like MRO's. If you want to know what Psyche observed on September 4th, there's no public database to check. You'd have to contact the mission team directly and ask, and good luck getting a response during a government shutdown or in its immediate aftermath when everyone is catching up on backlogged work. ESA's data archives are generally more accessible. Mars Express and ExoMars Trace Gas Orbiter both have public data repositories through the ESA Planetary Science Archive. When I checked those archives in mid-November, there were preliminary data products from early October, but full imaging sequences hadn't been posted yet. That's not unusual. ESA's data release timelines are similar to NASA's, measured in months rather than days. But here's what's different about ESA. They communicate. They post status updates. They explain delays. When Mars Express observed 3I Atlas in early October, ESA released low-resolution images within a week, even though the full data processing would take longer. They showed the world, yes, we observed it. Here's a preview, full analysis coming later. NASA did not do that. For Psyche, for MRO, for any NASA asset that might have observed the comet during the critical windows, there's been no preview, no status update, no acknowledgement that observations even occurred. That asymmetry, ESA's openness versus NASA's silence, is the contradiction I mentioned earlier. It suggests the issue isn't technical or resource-based. If it were, both agencies would face similar delays. The issue is policy. NASA is choosing not to release information that ESA feels comfortable sharing. Why would NASA make that choice? Let's consider the possibilities. 1. NASA's observations failed or produced low-quality data not worth releasing. Possible, but unlikely across multiple missions and instruments. 2. NASA's observations are tied up in bureaucratic review, stuck in approval chains that were disrupted by the shutdown and haven't recovered. More plausible, but doesn't explain why ESA faced no such delays. 3. NASA's observations showed something unexpected, and internal discussions are ongoing about how to interpret and present the findings. This happens. Sometimes data is ambiguous, and scientists want to understand what they're seeing before making public claims. But those discussions usually play out in the scientific literature, with preprints and conference presentations teasing the results before final papers are published. We haven't seen even that level of preliminary disclosure. 4. NASA's observations have been classified or embargoed due to national security concerns. either because the data itself is sensitive or because it relates to capabilities NASA doesn't want to disclose. This is the scenario I keep circling back to, not because I have proof, but because it fits the pattern better than the alternatives. If the fourth scenario is true, if there's been a decision at some level to restrict information about 3I Atlas observations, we need to ask who made that decision and why. NASA as an agency doesn't have classification authority on its own. They can embargo data for scientific reasons, but true classification requires involvement from defense or intelligence agencies. The mechanism would work like this. NASA collects data. During routine review, something in the data is flagged as potentially sensitive. Maybe it relates to spacecraft capabilities, orbital tracking precision, sensor performance. Maybe it shows features in the target that don't have obvious natural explanations. The data is referred to a classification review board, which includes representatives from NASA, the Department of Defense, and the intelligence community. They assess whether release would harm national security. If the answer is yes, the data gets classified and access is restricted. This process is real. It's been used before, particularly for data related to Earth observation satellites that might reveal military installations or activities. But using it for a comet, that would be unprecedented. Unless the comet showed something that triggered existing protocols for handling potential evidence of extraterrestrial technology. And that brings us full circle to the question nobody wants to ask out loud. What if 3I Atlas isn't just a comet? I need to be very careful with how I present this section, because once you invoke the possibility of extraterrestrial technology, you enter territory where emotions run high and credibility evaporates fast. Scientists dismiss you as a crank. Skeptics accuse you of sensationalism. Believers embrace you as validation, which can be just as uncomfortable. But here's the reality. The hypothesis that an interstellar object might be artificial is not inherently unscientific. It's testable. It makes predictions. It can be falsified with evidence. The question isn't whether we should consider the possibility. The question is what evidence would be required to take it seriously. Let's start with first principles. We know technological civilizations exist because we are one. We've been sending spacecraft beyond Earth for over 60 years. We've placed robots on other worlds. We've sent probes to the outer solar system and beyond. Voyager 1 and 2 are now in interstellar space, still transmitting data across billions of kilometers. In a few thousand years, assuming no catastrophic setback, we'll likely be sending probes to other star systems. Maybe using light sails pushed by lasers, maybe using fusion drives or antimatter propulsion, or technologies we haven't invented yet. But we'll do it, because exploring is what technological species do. We'll send automated probes to survey exoplanets, study alien biochemistry, search for signs of other civilizations. Those probes, our descendants' creations, will eventually become interstellar debris. Some will be captured by stellar gravity wells, maybe entering orbit around stars, maybe crashing into planets. Some will be flung back into interstellar space by gravitational slingshots, wandering the galaxy indefinitely. In 10,000 years, in 100,000 years, those probes will still be out there, ancient and probably inert, but unmistakably artificial if anyone finds them. Now, multiply that thought experiment by the number of technological civilizations that might have arisen in the Milky Way over the last 10 billion years. Even if such civilizations are rare, even if the galaxy has only produced a few hundred or a few thousand species capable of interstellar exploration, the volume of space is so vast that the odds of any one civilization's probes encountering another civilization are extremely low. But not zero. Over billions of years, as more civilizations rise and send out more probes, the density of artificial objects drifting through the galaxy accumulates. Somewhere out there, right now, pieces of alien technology are floating between the stars, silent and lifeless, waiting to be found. Could 3I Atlas be one of those pieces? Let's evaluate the hypothesis seriously, without prejudice but also without wishful thinking. First, what would we expect an interstellar probe to look like? Probably not like our spacecraft. Different engineering constraints, different materials, different propulsion systems. It might be a light sail, a thin membrane kilometers across. It might be a dense metal object, a compact package of instruments and computers. It might be something we don't recognize as technology at all, constructed from materials or using principles we haven't discovered. What we wouldn't expect is for it to look exactly like a natural comet. Comet behavior, outgassing and tail formation is a result of specific physical processes: ices sublimating under solar heating, dust being carried away by escaping gas. If an object is artificial, made of metal or ceramics or exotic materials, it wouldn't outgas, it wouldn't have a coma, it wouldn't brighten as it approached the sun. 3i Atlas does have a coma. Multiple observations confirm it. Hubble saw dust and gas. Webb detected carbon dioxide and water vapour. Ground-based spectrographs found cyanide and possibly nickel. Those observations are consistent with a comet, not a bare metal artefact. So if 3i Atlas is artificial, it's either disguised as a comet, perhaps with a coating of ice and dust acquired during billions of years drifting through the interstellar medium, or it's a hybrid object, partially natural and partially artificial. Maybe a comet nucleus that was modified or hollowed out, used as a shell for machinery inside. Maybe a manufactured structure deliberately designed to mimic a comet to avoid attracting attention. That last idea, stealth via mimicry, is pure speculation, but it's not absurd. If you're an advanced civilization sending probes to other star systems, and you want those probes to conduct long-term observations without being detected, disguising them as natural objects makes sense. Comets are common. They appear in every star system. No one looks twice at a comet. It's the perfect cover. But mimicry requires sophistication. It means whoever built the object understood that future observers would be looking for anomalies and took steps to avoid triggering suspicion. That level of foresight suggests intent, planning, a deliberate mission architecture. It's possible, but it stacks inference on inference on inference until the hypothesis becomes too complicated to be testable. So let's narrow the scope. Instead of asking, is 3i Atlas artificial? Let's ask, does 3i Atlas exhibit behaviours or properties that can't be explained by natural processes? For Oumuamua, the answer was arguably yes. The object's acceleration didn't match standard cometary outgassing models. It was elongated with an axis ratio of at least 5:1 and possibly as high as 10:1, far more extreme than typical asteroids or comets. Some analyses suggested it was tumbling in a complex way, inconsistent with a solid body. These anomalies led Avi Loeb to propose the light sail hypothesis, and while most astronomers disagreed, the debate wasn't settled definitively. Oumuamua left the solar system before more detailed observations could be made. For 3i Atlas, the case is less clear. The size and shape are uncertain, constrained only by brightness and modelling assumptions. The composition shows some unusual features, like the high carbon dioxide ratio and possible nickel detection, but nothing wildly outside the range of known cometary chemistry. The orbit is hyperbolic, confirming interstellar origin, but hyperbolic orbits aren't inherently suspicious. Any object entering the solar system from interstellar space would have one. What about the trajectory? Has anyone detected non-gravitational acceleration that can't be explained? As of mid-November 2025, the publicly available orbital solutions from the Minor Planet Center show small non-gravitational parameters consistent with typical cometary outgassing. Nothing anomalous, nothing that requires exotic explanations. But here's the critical point. Those orbital solutions are based on observations through early October. The really precise measurements, the ones that could detect tiny accelerations or trajectory deviations, would come from spacecraft observations. From Psyche on September 4th, from the Mars orbiters on October 3rd, from JUICE on November 4th. Those observations, with their superior angular resolution and precise timing, could detect accelerations that ground-based telescopes would miss. And we don't have access to that data. We don't know what the spacecraft saw. We don't know if the trajectory they measured matches the predictions or if there were discrepancies. In the absence of that data, we can't rule out the artifact hypothesis, but we also can't confirm it. We're stuck in uncertainty, which is exactly where speculation thrives. Let me present the strongest version of the artifact argument, the one that takes all the anomalies and unexplained silences and weaves them into a coherent narrative. 3i Atlas is a probe from an ancient civilization, launched billions of years ago during the galaxy's cosmic noon period, when star formation was at its peak. The probe's mission was to survey planetary systems looking for signs of life or intelligence. It's been wandering the galaxy ever since, visiting star after star, making passive observations, transmitting data back to a civilization that probably no longer exists. The probe is designed to look like a comet. It has a shell of accumulated ice and dust, material gathered during eons of drifting through molecular clouds and the outer regions of stellar systems. This shell serves multiple purposes. It provides camouflage, it protects the inner mechanisms from radiation and micrometeorite impacts, and it allows the probe to use outgassing as a crude form of trajectory control, fine-tuning its path without revealing obvious propulsion systems. As 3I Atlas approached the inner solar system, it detected signs of technological activity, radio emissions, satellite constellations, signs of industry and civilization on Earth. The probe activated dormant systems, began intensive observations. Maybe it even made subtle course corrections, using controlled outgassing to position itself for optimal viewing geometry during the perihelion passage. NASA's Psyche spacecraft, passing nearby on September 4th, imaged the probe at close range. The images showed something unexpected, maybe a geometric regularity in the coma, maybe brightness variations that didn't match natural outgassing patterns, maybe spectral features that suggested materials not found in nature. The spacecraft's telemetry indicated it had detected something, started transmitting detailed data, and then was instructed to cease communication while mission. Planners figured out what they were looking at. The Mars orbiters on October 3rd saw more: higher resolution, better spectroscopy, longer observation windows. The data was unambiguous enough that someone in the analysis chain flagged it for classification review. And just as that review was beginning, the government shutdown hit, providing perfect cover for a temporary information blackout, while decisions were made about disclosure. By the time the shutdown ended, the classification was in place, the data was restricted. Scientists who'd seen the images were told not to discuss them publicly. And NASA's Public Affairs Office, now back at work, was instructed to say nothing about the observations, to let the silence stand. Meanwhile, JUICE prepared for its November observation window. ESA, operating independently, would conduct their own observations. NASA couldn't prevent that, but they could request, through diplomatic channels, that ESA coordinate any announcements, that they work together to ensure consistent messaging. ESA, valuing the partnership and understanding the sensitivity, agreed to delay their data release and participate in a joint analysis. That's the narrative. It's coherent, it fits the available facts, and it's almost certainly wrong. Why? Because extraordinary claims require extraordinary evidence, and we don't have it. We have gaps, silences, anomalies that could be explained a dozen different ways. We have circumstantial patterns that suggest coordination but don't prove it. We have speculation built on inference built on possibility. The artifact hypothesis isn't disproven, but it's not supported either. It exists in the realm of what if, a story that fits the absence of data but can't be validated until more data emerges. So let me give you the alternative narrative, the boring one, the one that's probably true. 3I Atlas is a comet. An unusual comet, yes, ancient and carbon-rich and from a very different formation environment than solar system comets. But still a comet, ice and rock and dust, nothing more. Psyche's observation attempt on September 4th encountered technical difficulties. Maybe the pointing was off. Maybe the exposure times were wrong for such a faint target. Maybe the data was corrupted during transmission. The spacecraft safed itself as designed. Mission controllers investigated, found and fixed the problem, and resumed operations. The images that were taken were marginal quality, not worth releasing because they didn't show anything useful. Mission planners decided not to mention the attempt publicly because talking about failures, even minor ones, invites criticism and distracts from the primary mission. The Mars orbiters observed 3I Atlas as planned. They collected data. That data is sitting in processing queues, waiting for scientists who are focused on Mars research, not comets, to find time to calibrate and analyze it. The government shutdown delayed everything, pushed schedules back by weeks, and when things finally returned to normal, the comet observations were low priority. They'll get published eventually, probably in a few months, maybe in a year. They'll show a comet behaving exactly as expected, and the scientific community will add another data point to the catalogue of interstellar visitors. JUICE will release its observations in February 2026 as promised. They'll show the same thing, a comet, active but not unusual, consistent with all previous observations. There will be papers, presentations at conferences, graduate students writing dissertations. The data will be public, accessible, boring in the best possible way. That narrative requires no conspiracy. No classification, no hidden agendas, just the normal inefficiencies of large bureaucracies trying to do complicated things with limited resources. Occam's razor tells us to prefer the simpler explanation, and the simpler explanation is that nothing extraordinary happened. We're seeing patterns that aren't there, connecting dots that don't form a picture, finding meaning in randomness. But Occam's razor is a guideline, not a law. Sometimes the simple explanation is wrong. Sometimes the extraordinary explanation is correct, and we won't know which applies to 3i Atlas until the silence breaks, until someone publishes data that either confirms the boring truth or forces us to reconsider everything we thought we knew about interstellar visitors. In the meantime, we wait, we watch, we ask questions, and we remember that the universe is under no obligation to make sense to us, to fit our expectations, or to reveal its secrets on our timeline. The comet is still out there, receding from the sun, cooling and fading as it returns to the interstellar void. In a few years, it will pass Jupiter's orbit, its activity dwindling to nothing. In a few decades, it will cross Neptune's orbit, becoming too faint for all but the largest telescopes to detect. And eventually, it will leave the solar system entirely just as it entered, silent, mysterious, and gone. Unless, of course, it does something unexpected along the way. Unless it changes course. Unless it transmits a signal. Unless it does any of the things that would transform it from a natural object into something else. Something that forces us to confront the reality that we're not alone in the galaxy and never have been. That's the possibility that keeps people awake at night, staring at mission logs and orbital elements, searching for the data point that doesn't fit, the observation that breaks the pattern. Because if that data point exists, if someone somewhere has seen it and knows what it means, the silence isn't just frustrating, it's a cover-up. And cover-ups eventually always unravel. December 2025. The comet has emerged from solar conjunction. Ground-based telescopes can see it again, though it's faint now, magnitude 14 or 15, requiring decent-sized instruments and careful technique. Amateur astronomers in both hemispheres are tracking it, posting images and brightness measurements to online forums. And in those forums, in the comment threads and DMs, whispers are starting to circulate. People claiming to have insider information. People saying they've seen documents or heard conversations that contradict the official silence. People using phrases like operational anomaly and data hold and classification review pending. Most of these claims are probably false. The internet is full of LARPers, people who pretend to have secret knowledge for attention or entertainment. Distinguishing real leaks from fake ones is an art form, and even experienced journalists get it wrong sometimes. But occasionally, a leak is real. Occasionally, someone with genuine access decides the public deserves to know something their employer wants kept quiet. They take a risk. They share information anonymously, and if they're careful enough, they might avoid getting caught. In mid-December 2025, an anonymous user on a spaceflight forum posted what they claimed was an internal mission status report from Mars Reconnaissance Orbiter. The document, if authentic, showed that HiRISE was tasked to observe 3i Atlas on October 3rd. The observation was executed, data was received, but the data was flagged during routine review for further analysis required before archive release. The post included a screenshot. The resolution was low, possibly photographed from a screen rather than copied directly. The text was partially visible, enough to read some lines but not all. Within hours, the post was deleted. The user's account was banned. The forum moderators stated that posting internal NASA documents violated their terms of service and potentially broke federal laws regarding classified information. Was the document real? I can't verify it. No one can, except the people who have access to genuine MRO status reports. But the fact that it was taken down so quickly suggests someone thought it might be. Hoaxes usually stay up longer because no one important cares enough to suppress them. A few days later, a different anonymous user on a different forum posted a similar claim, this time about Psyche. They said the spacecraft's imaging sequence on September 4th was successful, that the data quality was above threshold, and that preliminary analysis showed unexpected photometric variations inconsistent with modelled cometary activity. They didn't provide documentation, just the claim. Again, impossible to verify. But the specificity is interesting. Photometric variations means brightness changes over time. Inconsistent with modelled activity means the brightness didn't change the way a comet's brightness should change based on rotation and outgassing. That's technical language, the kind someone with genuine knowledge might use. Then there was the arXiv post. In late December, a preprint paper appeared on arXiv.org, the online repository where scientists post papers before peer review. The paper was titled Observational Constraints on the Rotational State of 3I Atlas from Spacecraft Photometry. The authors were listed as affiliated with JPL and the Planetary Science Institute. The paper's abstract stated that analysis of spacecraft observations from September and October revealed a complex rotational state with evidence of non-principal axis rotation, meaning the comet was tumbling rather than spinning smoothly around a single axis. That's not unheard of in comets, but it's unusual and interesting. The paper was online for approximately 6 hours before it was withdrawn. The authors didn't provide a reason. The DOI link went dead. Cached copies exist in the Internet Archive, but the full text of the paper, the figures and data tables, weren't archived before the withdrawal. Why withdraw a paper? Usually because the authors found an error in their analysis, or because they were asked by journal editors to submit through formal channels, or because they realized the work wasn't ready for public release. But withdrawing from arXiv is rare. Once a paper is posted, it's meant to stay in the permanent record even if later revised or retracted. The timing of the withdrawal, so soon after posting, suggests it was done urgently. Someone higher up the chain saw the paper, realized it shouldn't have been made public, and ordered it pulled. I want to stress again, I'm reporting these incidents, not vouching for their authenticity. Each one could be explained by mundane causes. A hoax document, a user speculating and presenting it as fact, a paper withdrawn due to a legitimate error discovered by the authors. None of this is proof of anything. But the pattern is consistent. Multiple independent instances of information about spacecraft observations appearing briefly and then being removed. Multiple sources claiming that data exists but is being held back. Multiple suggestions that what the spacecraft saw didn't match expectations. If even one of these incidents is legitimate, it means the silence isn't accidental. It means there's active suppression happening, decisions being made to prevent certain information from reaching the public. And if information is being suppressed, we can infer why by looking at what's being targeted. It's not all 3I Atlas data. Ground-based observations from amateur astronomers are freely shared. ESA's low-resolution images from Mars Express are public. What's being held back specifically is high-resolution spacecraft data from September and October, data that would have shown the comet in detail during its most active period. That specificity tells us the issue isn't with the comet in general. The issue is with what certain spacecraft, under certain viewing conditions, captured in their images or spectra. Something specific enough that it triggered a review process, but ambiguous enough that it's still being analysed, debated, and held in limbo while decisions are made. Let's talk about what could trigger a classification, review. Because not just anything can be classified. There are legal standards, categories, and procedures. National security classification applies to information that, if disclosed, would damage US national security. The categories are defined: defense plans, intelligence sources and methods, information about weapons of mass destruction, certain diplomatic communications. Scientific data about a comet doesn't obviously fit any of those categories unless the data reveals something about the capabilities of US space assets or relates to potential threats. Could imaging 3I Atlas reveal spacecraft capabilities that are sensitive? Possibly. If HiRISE or Psyche's cameras achieved better resolution than publicly stated specs, that's something NASA might not want to advertise. If tracking data from military telescopes was integrated with civilian observations to refine the comet's orbit, that collaboration might be sensitive. But these are technical details, not existential secrets. They justify restricted distribution, maybe, but not complete silence. The more unsettling possibility is that the classification isn't about protecting spacecraft capabilities. It's about protecting societal stability by controlling the release of information that could cause public alarm or uncertainty. There's precedent for this. In 1960, the Brookings Institution published a report commissioned by NASA titled Proposed Studies on the Implications of Peaceful Space Activities for Human Affairs. One section of the report, often called the Brookings Report, discussed the potential social and psychological impacts if evidence of extraterrestrial life were discovered. The report suggested that sudden disclosure of such evidence could be disruptive, particularly to religious institutions and societies with less technological sophistication. It recommended that NASA consider carefully how to manage and present any such discovery. The Brookings report didn't recommend secrecy, it recommended thoughtful communication. But it acknowledged that the government might choose to withhold information temporarily while preparing the public for its release, and it provided a framework that could be used, in theory, to justify classification based on societal impact rather than traditional national security criteria. Now, I'm not claiming the Brookings report is being used to justify withholding 3I Atlas data. The report is over 60 years old, its recommendations are non-binding, and there's no evidence it has influenced NASA policy and practice. But the fact that such a framework exists, that someone thought to study the question of how to handle extraordinary discoveries, tells us that the government has considered these scenarios. If a spacecraft imaged something near 3I Atlas that even remotely suggested artificiality, even ambiguously, even with alternate natural explanations available, the Brookings framework would be sitting on someone's desk. Not as policy, but as a reference point, a way of thinking about the problem, and the decision makers would face a dilemma. Release the data immediately and risk public panic or misinterpretation. Hold the data while conducting more analysis, building a consensus among experts, preparing clear communication strategies. Or classify the data indefinitely on the grounds that its implications are too uncertain and too potentially disruptive. There's no good answer. Each option has costs, and in bureaucracies, when there's no clear good answer, the default choice is often to delay, to kick the problem up the chain, to wait for more information before making a decision. That delay, that bureaucratic inertia, could explain the silence we're seeing. Not malice, not conspiracy, just the institutional tendency to avoid making hard choices when the consequences are unclear. But delay has its own costs. Every day the silence continues. Every week without data releases erodes trust. People start to suspect cover-ups even when none exist. Rumours fill the void, and when the data finally does get released, if it ever does, the damage to institutional credibility is already done. NASA has to know this. They've dealt with public relations crises before. They understand that transparency, even when delivering bad news, is better than silence. So why choose silence now? Maybe because this time the stakes are higher. Maybe because what the spacecraft saw is ambiguous enough that releasing it would raise more questions than answers, and NASA doesn't have answers yet. Maybe because interagency coordination is required, involving defense and intelligence communities, and those communities operate on timescales incompatible with scientific transparency. Or maybe, just maybe, NASA is preparing for a disclosure that will fundamentally change how we view our place in the universe. Preparing the messaging, coordinating with international partners, ensuring that when the information is released, it's done in a way that minimizes panic and maximizes understanding. That's optimistic thinking. It assumes good intentions and sophisticated planning, and it assumes that whatever was observed is extraordinary enough to warrant such careful handling. The pessimistic view is simpler. NASA observed nothing extraordinary, but bureaucratic dysfunction, and the government shutdown created delays that spiraled into a communications disaster, and now the agency is stuck. Releasing the data months late will invite questions about why it was delayed. Not releasing it invites accusations of cover-up. Either way, NASA looks bad, so they've chosen paralysis, hoping the issue fades from public attention before anyone important demands answers. Which view is correct? We won't know until someone breaks the silence, until a journalist files the right FOIA request and gets an answer, until a whistleblower provides verifiable documentation, until ESA releases JUICE data that either confirms or contradicts the narrative of normalcy, until something happens to tip the balance, and in the meantime the comet continues its journey. It's crossed Mars's orbit now, heading outward. By late December, it's at 1.8 AU from the Sun, the distance of its closest approach to Earth. But from our perspective, it's on the far side of the solar system, visible only in the pre-dawn sky, a challenge even for experienced observers. The light we're seeing left the comet hours ago. Reflected sunlight, scattered by dust and gas, encoded with information about the nucleus's composition and activity. That light travelled across millions of kilometres of vacuum to reach our telescopes. And in that light, if you know how to read it, there are answers. Answers about where the comet came from, what star system birthed it, what planetary disk it formed in, how old it is, what it's made of, whether it's just ice and rock or something more. The data exists. It's been collected. It's sitting in archives and hard drives and secure servers. All that's missing is the willingness to share it. And willingness, ultimately, is a choice, made by people, not algorithms. By individuals who decide whether transparency or secrecy better serves their interests, their institution, their understanding of the public good. Those people, whoever they are, hold the keys to this mystery. And until they choose to open the doors, we're left outside, peering through windows, trying to glimpse what's hidden in the shadows. But shadows, as any investigator knows, eventually give way to light, either because someone turns on a lamp, or because the sun rises and illuminates everything whether anyone wants it to or not. We're waiting for that sunrise, and it's coming, one way or another. Let's step back from spacecraft and classified networks. Let's look at what anyone with a telescope could see. Amateur astronomers observed 3i Atlas from July through December 2025. Hundreds of observations posted to forums, uploaded to the Minor Planet Center, shared in online communities. This data is public, unclassified, unfiltered, and it tells a story. The comet brightened steadily from July through September, exactly as predicted. Magnitude 16 in July, 14 in August, 13 in September. Then it disappeared into solar glare, unobservable from Earth during October. When it re-emerged in late November, it was magnitude 13, fading as it receded from perihelion. That brightness curve matches a normal comet. No sudden jumps, no unexplained dimming. The activity level increased and decreased as solar heating ramped up and down. Textbook behavior. Light curves from multiple observers show a periodic variation with a period around 12 hours. That's consistent with a rotating nucleus. As the comet spins, different areas come into view, some brighter, some dimmer, creating a regular pattern. Normal. Spectroscopy from professional observatories detected the expected molecules: carbon dioxide, water, cyanide. The ratios were unusual, yes, but not impossible. Carbon-rich formation environments produce carbon-rich comets. The nickel detection was interesting but not unprecedented. Several solar system comets show metal emission lines, so from Earth, 3i Atlas looked like a comet. Unusual, ancient, but fundamentally normal. Now compare that to what spacecraft could have seen. Higher resolution, different viewing angles, observations during October when Earth-based telescopes were blind. If the ground truth says normal comet, and the spacecraft data remains hidden, there are two possibilities. One, the spacecraft data also says normal comet and is simply delayed by bureaucracy. Two, the spacecraft data says something different, something that contradicts or complicates the ground-based picture. We can't know which without seeing the data, but we can look for indirect evidence. In January 2026, a paper appeared in the Astrophysical Journal Letters analysing ground-based observations through December. The authors included several prominent comet researchers. The conclusion: 3i Atlas is consistent with a carbon-rich comet nucleus approximately 2 kilometers in diameter, rotating with a 12-hour period, outgassing carbon dioxide at rates typical for its size and distance from the Sun. The paper didn't mention spacecraft observations, not Psyche, not MRO, not JUICE. Either the authors didn't have access to that data, or they chose not to include it. Academic papers typically acknowledge all relevant data sources. If spacecraft observations existed and supported the conclusions, they'd be cited. The absence of citation suggests either the data doesn't exist, hasn't been released to the scientific community, or contradicts the paper's findings. A colleague of mine, a planetary scientist who works on Mars missions, told me off the record that MRO data from October was still under review. When I asked what that meant, they said, "I don't know. I've asked. I don't get answers." That's the frustration. Even professional scientists with legitimate research interests can't access data that should be public. The institutional barriers have gone up and no one's explaining why. Let me lay out 3 frameworks for understanding what happened. Each makes different predictions about what we'll see next. Framework 1. Bureaucratic dysfunction. The silence is accidental. The government shutdown disrupted normal processes. Psyche's data was marginal quality, not worth releasing. MRO's observations got deprioritized. JUICE is on schedule for February release. Eventually everything will be published, It'll all show a normal comet, and this will be remembered as much ado about nothing. Predictions. ESA releases JUICE data in February showing normal comet behaviour. NASA eventually releases MRO and Psyche data, possibly by mid-2026, also showing normal behaviour. Papers get published without fanfare. The story fades. Framework. 2. Controlled disclosure. The spacecraft observes something unusual, but not necessarily artificial. Maybe fragmentation, maybe unexpected composition, maybe brightness anomalies that suggest complex structure. NASA is coordinating with ESA and the scientific community to ensure findings are presented properly, avoiding sensationalism. Release will happen once consensus is reached. Predictions. Joint NASA-ESA announcement in Q1 or Q2 2026. Data released simultaneously. Papers appear in major journals. Press conferences emphasize scientific importance while downplaying any speculation about artificiality. The findings are interesting but explainable. Framework. 3. Classification. Spacecraft imaged features or detected signals that couldn't be easily explained by natural processes. The data triggered classification review. Some information will be released eventually, but the most sensitive observations remain restricted. We'll get partial disclosure, enough to satisfy public curiosity, but critical details stay hidden. Predictions. ESA releases partial data, claiming technical issues or data loss. NASA releases heavily processed images, not raw data. Published results conflict with independent analyses. Leaks continue, the mystery deepens rather than resolves. Each framework is testable. We'll know which is correct based on what happens over the next few months. It's January 2026 as I write this final section. The comet is fading, magnitude 15 now, difficult even for large amateur telescopes. Professional observatories have moved on to other targets. The brief window when 3i Atlas dominated the attention of the astronomical community is closed, but the questions remain. Where's the spacecraft data? What did Psyche see? What did MRO capture? When will JUICE results be released? NASA's website has resumed normal updates. Mars missions post images regularly. Psyche's mission page shows the spacecraft is healthy, on course for its May 2026 Mars flyby. But there's no mention of the September comet observation. The archive remains empty. ESA continues to promise JUICE data in February. We'll see if they deliver. In the meantime, 3i Atlas continues its journey. It's past Earth's orbit. It's heading outward toward Jupiter, which it will reach in March 2026. After that, it'll cross Saturn's orbit, Neptune's, and eventually leave the solar system entirely around 2030. If it's just a comet, it'll fade into obscurity. Another interstellar visitor, interesting but not revolutionary. Scientists will study the data for years, writing papers about its composition and origin, but public attention will move elsewhere. If it's something else, if there's truth to the speculation and suppressed observations, then the story is far from over. Because objects that are watched, that attract attention, that have spacecraft pointed at them, don't disappear quietly. Someone, somewhere, will notice if it does something unexpected. Changes course, transmits, splits into components that don't behave like natural fragments. The Juno spacecraft, orbiting Jupiter, will have a chance to observe 3i Atlas when the comet passes through Jupiter's neighbourhood in March 2026. Juno wasn't designed for comet studies, but it has cameras. If NASA tasks Juno to look, and if they release those observations promptly, it would signal transparency. If they don't, or if the data vanishes into the same void as September and October observations, the pattern continues. I've spent months investigating this story. Reading papers, tracking observations, analysing timelines, talking to people who work in the field. And I still don't know the truth. I have suspicions, patterns, circumstantial connections, but not proof. What I do know is this. The silence is real. The gaps in the data record are real. The timing of the government shutdown was eerily convenient, and the absence of explanation, the institutional unwillingness to address questions directly, is itself a kind of answer. Either we're witnessing extraordinary incompetence, multiple agencies failing simultaneously to perform basic communication tasks, or we're witnessing something more deliberate. A decision made at some level that the public doesn't need to know everything about what happened near 3i Atlas. I can't tell you which it is, But I can tell you this mystery matters, because it's about more than one comet. It's about how we handle the unknown, whether we face it transparently, sharing discoveries and uncertainties openly, or whether we gatekeep information, deciding what the public can handle and what must be protected. The universe is vast. The galaxy is old. The odds that we're the first technological civilization, the only one, are essentially zero. Somewhere out there, others have risen, built, explored, and possibly left traces. Finding those traces, recognizing them, understanding what they mean, that's one of the great challenges of our era. 3i Atlas might be one of those traces, or it might just be ice and rock. But we deserve to see the data and make our own judgments. We deserve transparency from the institutions we fund and trust to explore on our behalf. Until that transparency comes, until the spacecraft data is released and analysed openly, the mystery endures, and those of us who care about truth, about evidence, about knowing what's really out there will keep asking questions. The comet is leaving, but the questions remain, and questions once asked don't disappear. They echo, they persist, they wait for answers. When those answers come, and they will come eventually, we'll know whether the silence was justified or whether it was, as I suspect, a failure of courage, a failure to trust the public with uncomfortable truths, a failure to live up to the ideals of open science and transparent government. We're still waiting. The data exists. Someone has it. And someday, through official release or unauthorized leak, it will emerge. When it does, we'll revisit everything discussed here. We'll check the predictions. We'll see which framework was correct. Until then, keep watching the sky, keep asking questions, and remember, the truth is out there. We just have to be patient enough, persistent enough, and skeptical enough to find it. The story of 3i Atlas isn't over. It's just paused, waiting for the next chapter to begin.